Hello everybody, and thank you for attending this presentation. I am Ignacio, mechanical engineer and project manager from INCOSA, and I want to present the research carried out with my colleague Javier Perez-Mas from Geoconsult about CFD and evacuation simulations for 3 railway tunnels, and more specifically about the challenges in case of natural ventilation. This presentation is structured in 4 different parts. First, I will give some context about the works and the methodology. Then, we will go through the simulation hypothesis and input data. And finally, we will see the results and overview some conclusions. So, let's start with the introduction. Although they are not common, the train fires inside tunnels can be catastrophic due to some specific aspects, such as the heat release rate, the number of passengers to evacuate, the absence of mechanical ventilation in the tunnel, and the reduced space for the evacuation compared to other types of tunnels. Some of these aspects are becoming less relevant as the technology improves, especially those related to the materials of the train, as the heat release rate, the toxicity of the smoke, and the smoke generation itself, that are dramatically reduced by the application of modern standards such as the European standard EN 45545. Nevertheless, there are still many risks associated to fires in railway tunnels, and getting and sharing knowledge about this topic is still relevant and useful. In accordance with the previous introduction, this modest research intends to give some light about some of them, taking advantage of the works performed for the natural ventilation studies of 3 different tunnels. Originally, the ventilation studies of the 3 tunnels were different and isolating about them. But as the methodology employed was the same and the input data are similar and comparable, it was decided to put them together in order to try to get some conclusions from the risks associated with the absence of mechanical ventilation in railway tunnels. Here we can see the main characteristics of the 3 tunnels: the cross-section, the width of the evacuation walkway, and the slope of the tunnels. The methodology considered for the studies was based on the comparison of AZ and RC times, which is a well-known procedure for performance-based design. In this case, there were some differences regarding the implementation of this methodology in other buildings, as the space and movement possibilities for the evacuees are lower than in other kinds of scenarios. This will be explained in detail in the following slides. Basically, the AZ time was obtained from CFD simulations made with PyroSim, and the RC time from simulations made with Pathfinder. Now, we are going to see some relevant aspects related to the simulation hypothesis and the input data. In the cases simulated, the input data for the model was divided in 4 different groups: the geometry of the model, which is imported from 3D modeling and was already defined, the fire characteristics, which were defined for the simulation based on the data for the trains that can use these tunnels, the boundary conditions, defined according to local temperatures, wind, and pressure differences between tunnel portals, and the evacuation parameters, considering the population, the pre-movement times, and the walking speeds. The geometry for the tunnels is extremely relevant for the results, as parameters such as the cross-section and the height of the tunnel are directly related to the height of the smoke layer. Additionally, the slope of the tunnel plays an important role, impelling the smoke in the direction contrary to the slope, in what is known as the stack effect. Finally, the last geometric parameter to consider is the distance between emergency exits. In railway tunnels, it is considerably longer than in road tunnels, and it can vary substantially between different railway tunnels, making each case a singular one. The fire characteristics are determinant for the development of the simulations. In the scenarios studied, as they were developed for Spanish tunnels, the heat release rate curve was taken from the Spanish standard IFI, which gives instructions for the design of the railway tunnels, including the heat release rate curves to be used in case of passenger trains, freight trains, and dangerous goods trains. The case of two trains inside the tunnel was not considered, and consequently, in terms of ventilation and egress, the worst case was a fully loaded passenger train, so the value of 15 megawatts was considered. It has to be noted that the simulation begins when the train has stopped in the tunnel, and consequently, the heat release rate at the beginning of the scenario is not zero. It's about 2 megawatts. Finally, regarding the material considered, it's a common practice in trains, more in medium-age ones, to have fewer glass-reinforced plastics, and more specifically, polyester. Therefore, and considering that not all the trains that will use the tunnels will comply with the latest standards, polyester was considered as the burning material, obtaining the burning properties from the SFPA handbook. When assessing the smoke layer within the tunnel, the ambient temperature and internal tunnel temperature are key factors. Therefore, data from weather stations close to the tunnels were used to establish the baseline conditions. For external environment, it was considered the 5th percentile of recorded temperatures as the reference point. Inside the tunnel, the wall temperature was determined based on the average temperature during January, the coldest month. This approach is critical, as lower temperatures can lead to increased mixing of the smoke, which in fact can complicate the evacuation efforts. Additionally, the pressure difference between the tunnel portals was critical, as it can move the smoke in the same direction than the slope, or in the contrary one. The pressure difference is influenced by the external wind and the height difference between portals. This was calculated according to local data measured by weather stations. Regarding the evacuation parameters, the key factors are the total number of people, the speed at which they will be able to move around the scenario, and the distribution of population. In each of the three scenarios, the occupants will be situated between the tunnel compartments, with no people present in the tunnel at the beginning of the simulation. Regarding the occupant capacity, an evaluation of various train models that operate through these tunnels was conducted. The model selected for simulation purposes considers the highest capacity, which up to 730 passengers in a double train configuration. An example figure of this train can be seen on the slides. The population characteristics are mainly defined by the size of the agents and the walking speed. The walking speed was taken from the International Maritime Organization IMO guidelines for evacuations. The population distribution was considered from the investigation report, evacuation analysis in high-speed trains based on computer modeling and simulation from the IDAI group of the University of Cantabria, which is a reference in Spain for this kind of study. In addition to the evacuation parameters already seen, three specific considerations were made. In first place, as there was a remarkable step from the train floor to the evacuation walkway, a speed reduction factor of 0.5 was applied to this stair in order to consider the difficulties for the different kind of people to exit the walkway. In second place, it is acknowledged that walking speed is reduced when visibility falls. For these simulations, it was used the speed reduction curve included in PyroSim, coming from the studies of Friedel et al. Nevertheless, other studies included also the lighting level as a factor for the correlation between smoke presence and walking speed. This consideration could be also a possibility for future evacuation studies of controlled environments such as tunnels, in which the requirement of lighting levels at the walkway are very well defined by the standards. Finally, for pre-movement times, alarm recognition response time, it was considered that the public address system of the trains, as well as the presence of train assistants inside the train, would lead to a negligible pre-movement time. Even more, considering that a fire which leads to a train detention in a tunnel, which is highly improbable, should be detected long time before the train is stopped, and consequently, onboard staff will be warned. Finally, and before showing the results, this slide shows a summary of the three scenarios. Scenario 1 has a bigger cross-section than the rest, and a lower pressure difference between portals. And scenarios 2 and 3 are very similar, with differences in the evacuation direction regarding the slope and the stack effect. In scenario 2, it is unfavorable for the evacuation, and in scenario 3, it is better for evacuation. Now, it's time for the results of the scenarios. For all the cases, measures were taken 2 meters high from the evacuation walkway. In first place, we are going to talk about temperature. As it was previously explained, the boundary conditions imposed were those from the coldest month, January, so the maximum temperatures due to the fire are low. Consequently, temperature differences are analyzed. It can be seen that in scenario number 1, the temperature increase is the lowest from the 3 tunnels. This is logical, as this is one with the biggest tunnel cross-section. Regarding the scenarios 2 and 3, the second one is the hottest, as the cross-section is reduced and the smoke is impelled in a natural way towards the evacuees. Finally, scenario 3 is in a middle point between the two previous, having a reduced cross-section, but with the stack effect not impulsing the smoke towards the evacuation pathways. Now, let's see the visibility. The 3 scenarios present a similar behavior regarding the visibility, with some little differences. In all the cases, it falls below the common limit of 10 meters considered for normal evacuation, as for example in standard NFPA 130. In the first case, as the tunnel cross-section is bigger, the visibility is reduced less than in the rest of the cases. The scenario 2 shows the lowest visibility, being about 1.5 meters. Finally, scenario 3 has a very low visibility of about 2.5 meters, slightly greater than scenario 2 due to a favorable stack effect. Including the thermal radiation, all the scenarios have a low impact on the evacuation passengers. It's remarkable that in the case of the second scenario, with a narrow geometry and the smoke impelled towards the evacuation path, it reaches about 110 watts per square meter, which is quite lower than the limits commonly considered. It has to be noted that the first meters around the fire are not considered for the measurements, as they would distort the global. Finally, the poisoning measurement, the fraction effective dose. For the 3 scenarios, it has been computed by Pathfinder based on the results from PyroSim, and these results are corresponding to the most poisoned passengers. It can be seen in all of them that none of the scenarios have problems regarding the FIDs. Once shown the results, it's the time to discuss the conclusions reached in the analysis of the 3 cases present. The analysis of the 3 scenarios revealed that the absence of mechanical ventilation in the tunnels leads to the restrictive outflow of smoke and reduces significantly the visibility along the evacuation walkways. This reduction was more pronounced in tunnels with smaller cross-section, as is natural. Other tenability parameters analyzed, such as thermal radiation, temperature, and fractional effective dose, remain well below commonly accepted limits across all the scenarios. Therefore, we can conclude that the primary risk during the evacuation in all the cases was the lack of visibility and consequently the associated fried products not accounted in the FIDs. And finally, let's raise some conclusions. For railway tunnels serviced by older trains, mechanical ventilation is essential due to the significant impact of smoke on visibility. If necessity or not, for each individual case, should be analyzed by means of engineering tools. If mechanical ventilation can't be installed, alternative mitigation measures should be considered to assist users in reaching emergency exits. These measures, as shown in the slide, may include low-height lighting, handrails, backlight evacuation signs, light beacons, or other similar mitigation measures. Thank you for your attention, and now it's time for the questions. I will try to solve all the doubts regarding these little research. Thank you very much. Regarding the occupancy groups, what was the reference of those assumptions? Okay. In this case, it was a little bit easy because, okay, and there's a second question. In Spain, there was a study about the percentage of people, of different groups of people that usually use the train, the long distance train. So in this case, it was easy to get the information. Regarding the percentage for the handicap, in this case, they were not considered because these kind of trains originally were not prepared for this kind of people. But I have to say that now modern trains are considering at least one handicap place for in each train, or two, depending on the size of the train. So probably these kind of studies should be done again, considering the people with reduced mobility. But one appointment regarding the people with reduced mobility, they already were considered. People with reduced mobility were considered. People on wheelchair were not considered. And well, regarding the other question, a different way. The pre-travel time in this case was considered to be 0 from the moment the train stops. I mean, in case of having a fire in a train that finally gets stopped in a tunnel, many things have failed. So the staff in the train, because there's always staff because they are long distance trains, will be warned and they will have activated the protocol. So the only time considered was from the stop of the train in the tunnel, 30 seconds considered for the opening of the doors and the deployment of the little stairs from the train to the walkway. Okay.
Okay, thank you. So just for the room, the first question, I think, Jose, we missed the answer to that. We weren't quite up live here in the room. So the question was regarding the occupancy groups, what was the reference for those assumptions? And I think you had mentioned that from the IMO standard. And then, is that correct?
Yes, okay. Yes, the IMO was used for the data for travel speeds, but the amount of people for each group and age, gender and age, was taken from a previous study from the Spanish government in collaboration with the University of Cantabria, which considered the different amount of people that usually make use of the trains, long distance trains.
Okay, thank you for that. And then just for the room, the answer we got kind of mid-session was about considering the percentage of handicapped or disabled population. And then the last was the pre-travel time was considered for the first percentile or based on the 99th, and that was after train stop, 30 seconds, and then that was kind of your pre-movement delay, right, with the evacuation?
Exactly, that is it.
Okay. Did you use any distribution on the pre-movement time for the train, or was it just everybody starts at 0 and starts to evacuate?
Well, in this case, we assume that the public address of the train and the collaboration of the staff were enough to, once the train was stopped, the people would start to move. In other cases that we have simulated for trains without public address or without staff, like for example underground or metro, we usually consider the pre-travel time for people from the British standard, the PT document.
Okay, good. Questions here in the audience? Kevin here.
You may have mentioned it, but I don't remember what it was. Where did you get the soot yields to use in the simulation?
Okay, if I'm not wrong, we obtained it from the SFPA handbook.
Okay, for what was the assumed combustible or fuel?
Yes, we considered fiberglass reinforced polymer. In this case, I think it was polyester.
Okay, thank you.
Anything else? One in the back here.
Hi, did you account for the slope on the movement of the occupants as they evacuated?
Good question. Yes, as we did the combination of scenarios between the PyroSim FDS and Pathfinder, we took into account the little slope in this case. In any case, we have to consider that the slope for people was low because the train this kind of tunnels usually have less than 3% of slope or even less, but it was more relevant for the smoke. But in any case, we consider it, and a little, very little speed reduction was automatically considered for these people.
So some speed reduction on the navigation surface in Pathfinder. Is that how you implemented that?
Exactly, that's
okay. Anything else? No? Okay, well, thank you very much for joining us live and for the talk. And we can follow up with more questions later if we have them. Thanks, Jose.
Thank you, everybody. See you. Cheers.